Hello everyone, this is Sam from HivePy. Today we're going to be taking a look at support vector machines. These are supervised algorithms, which we take a number of data points which are categorized, and then we just find some line or some plane, or hyperplane, I guess, if you're working in 4 dimensions or more, which separates the two data categories as best as possible. So it's similar to k-nearest neighbors, because in the end we're going to get some kind of grand categorization machine, but this requires the data to be separated a little bit more, and it also works a little bit worse on multi-dimensional data. There's a load of positives and negatives between the two, and to be honest, those are all online, and I don't really have time to explain them here. I'm just going to give you a very brief example of what the algorithm is and how to apply it at a very base level. So, support vector machine algorithm. We want to split the data into two, so all these black lines accomplish that, but which is the best black line, and what metric are we going to use to measure which is the best black line? For support vector machines, we're going to be looking at the margin between these black lines and the data points. So here we can see that this black line has a very small margin here, so it's not as good as this black line, which has a larger margin here. We're also going to be looking at the kind of the maximal minimal margin. So you might say that this line has a very big margin here between this and the green point, but unfortunately it doesn't have a very good margin for the red points. We wouldn't count this as better than these two. So we're going to be looking at kind of like what gives us the best kind of worst margin between the two. And if I scroll down here and we spoil the kind of guide a little bit, we eventually will be able to get a margin like this, where we have a nice equal margin that is quite kind of maximal between the two. So how do we use this in real life? Drag this over here. Sorry about that. We're going to be using this for an example, and then you're going to go on and use it in a mini project which is to do with real data. It's to do with real cancer data for breast cancer patients, and you're just going to be splitting those up into cancerous and non-cancerous, or I think it's malignant and benign tumours. So for the example, we're going to be importing our first example, CSV, which is going to be support vector machines.csv. And then we're going to be looking at the head of this. So we can see in the head we have the classes, the X data and the Y data. If I change this to tail, we'll see we have the class being 1, so we have 2 classes that we're interested in. Then, as with the k-nearest neighbours, we are going to be looking at points and classes. I'm going to do this in a slightly different way to how we did it in the k-nearest neighbours, and you might prefer this. We're just going to list the X data and the Y data columns. So we have X data, Y data, Y data, and then we're going to do dot as matrix. So this is the same kind of way of well, it's a different way of achieving the same thing as the df.drop class axis equals 1. Here we're just, instead of dropping a column, we're just getting 2 columns. So I'd say dropping the data column might be faster in a case where we had millions of columns, but we don't really need to do that, so we can make things a little bit easier on ourselves. I'm just going to say classes equals df class, because that's what our classes are. And then it's super duper simple now. We just go svm equals svm.svc kernel equals linear. So what this is doing, SVC is kind of like the type, it's a support vector categorization, and we're going to be doing it with a linear kernel, so which means that we want to be looking at a line and not like some weird kind of wiggly line or anything else. We're only interested in a linear kernel, and then we are going to fit this. So dot fit points and classes. I haven't spelled classes right. Okay, there we go. And then from here, what we can do, if we just type in this and we get an error because we don't have classes, that's because this is df.class, not classes. That should work. There we go. And from here, we can actually predict. Well, first off, I'm going to go SVM just to look at what's happening here. We have C cache. We have a kind of weight size coefficient. We have loads of different things which you can look into if you want to look further into this. The C and the cache size, that's to do with like if we change these, we can kind of get different accuracies of our model. which is something you can look into. It's quite interesting as well, but we don't really have time here, and it would take a very long time to explain. There's like a whole book of stuff. But from here, we can do some interesting things like predict stuff in the model. So we haven't actually called our model here. We've called SVM. So svm.predict, and then we're going to pass a list of lists, and the lists are going to be our points. We have 6, 1, and 1, 6, 1, 6. And we will see we get 1 and 0. So this point here would be expected to fall into the second class, and this point here would be expected to fall into the first class. So I'm going to quickly come back to the guide here. And you can see this is just what I've been working off. In the guide, and I'd really recommend you look at this, we can do a similar thing to k-nearest neighbours, and this is actually just taken from the k-nearest neighbours guide because the code is so similar. We can see that we actually get a graph of what's going on. We can see the line here of the categorization, so anything that falls in the red will end up being categorized as red, and anything that falls in the green will be categorized as green. We can also graph using a little bit of weird mathematics. We can graph the actual margins and what's going on here. And we can also see the mini project. So the mini project here is we import some breast cancer data from the sklearn datasets, and we're going to be trying to categorize using support vector machine categorization whether a test tumor, which we have here, is malignant or benign. So we have a load of different metrics here. So we're actually going to be working in, what is this, 1, 2, 3, 4, I can't be bothered to count this, it's like 30 dimensional space, and then we're going to be trying to split this up into two spaces, malignant and benign tumors. So the theory behind this in terms of the dataset is that all the kind of malignant kind of tumors will have very different attributes to benign tumors, so we can use this algorithm to kind of cut down the middle and then split the two categories in two, and then when we get a new tumor we can definitively say which one is which. So hopefully that's fun and interesting. Next time we'll be looking at a different machine learning algorithm, and hopefully I'll see you then.